All right, so now I'm going to look at finding some definite integrals. And generally what we'll do is we'll find an exact value. But if you think about exact values for trig, the bounds, what kind of numbers do they need to be? Because when you think about like, sine 2 and you try to put that in your calculator, it's going to get you a lot of decimals. How do I get like a nice number out of sine? Well, if I do like sine pi on 2, for example, that gives you a nice number. It gives me 1, right? So the idea is that I can actually look at my bounds in terms of pi to get something that's quite nice. So that's what we're going to look at in these problems here. So let's look at this first one. I'm going from 0 pi on 2 for cos of x. And so at this point, I just want to stress that it's so important that we're comfortable working with radians here and your exact values. If you're not too comfortable with it, now is the time to kind of address that because it's not going away anytime soon, unfortunately. Trig and the exact values just kind of creeps into all these different kinds of topics. So let's look at this one first. So let's go look at my form. Okay, which form does it match up with? Well, if I want to integrate cos, I know that becomes sine. So I'm going to go ahead and do that. Now that I've got bounds here, I'm going to use my square brackets. I'm going from 0 to pi on 2. And hang on, that's convenient, isn't it? It's the same one that I was looking at over there. So I'm going to substitute in my x values. Sine pi on 2 minus sine 0. It gives me quite a nice area. It's going to give me 1. Yeah, okay, so nothing too much I have to worry about that. Because that one I could put in my calculator actually, because it's going to be like an integer. But we just have to be careful because when you get stuff like this, for example, let's do it over here. Let's have a look at this guy. So the integral of sine of x from pi on 4 to pi on 2. So we have to be careful when we look at stuff like this now, right? Because what I want to do is, I know that this is going to be the integral of sine, which comes to negative cos. And so I can go ahead and do that. That's going to be the negative, I'm going to just pull out to the front, right? So it's going to be negative cos from pi on 4 to pi on 2. And so you want to be comfortable with your exact values here. And I want to write them all out first. So I've got cos of pi on 2 minus cos of pi on 4. And you can think about this graphically, or you can use your triangles. You've got a few different options, right? So here's my cos. And so when I take cos of pi on 2, that's just going to become 0. And when I take cos of pi on 4, that's going to become 1 on root 2. So I've got negative 1 on root 2. That just becomes positive 1 on root 2 for that one there. All right, here's another one. We're working with sec squared, which we've seen before. We know that's just going to be tan when we integrate. But here I want to pull out some constants. So I've got 5 that I'm going to take out. Again, just getting comfortable with these like exact values I'm going to be working with. Because when I integrate this, I'm going to end up with 5 outside of, this is going to be tan x now, from pi on 6 to pi on 3. And so I'm actually going to substitute these in as well. So tan of pi on 3 minus tan of pi on 6. And just think about your exact value. So tan of pi on 3, that becomes root 3. And tan of pi on 6, that just becomes 1 on root 3. And your textbook will probably do some simplification after that as well, like bring them under a common denominator or something, but I'm happy for you to just leave it like that for now. All right, so again, we just want to make sure we're very comfortable with our exact values as we're doing this. So here I've got 2, I'm going to take that out. So I get left with cos of 3x from pi on 6 to pi on 4. And so what form is this? Well, it's matching up with this one at the moment. And so when I take that, I've got an a value here, which is 3. So that's also going to be a part of that. And then when I integrate, I'm going to get sine of 3x from pi on 6 to pi on 4. And this is why I say you need to be very comfortable with the exact values, because what happens is that with something like this, we're going to have to actually evaluate stuff that's beyond the first quadrant even, right? So if I put x as pi on 4, I get 3 pi on 4, I just multiply it together. And if you're going to get sine of 3 pi on 6, that's actually pretty fortunate. That's a nice value. That's 3 pi on 6. That's just the same as pi on 2 when you simplify, because 3 on 6 is just half, right? And so here, what I'm going to get is sine 3 pi on 4. A few ways you can think about that. What I tend to do is I tend to think about that in terms of degrees, right? So to convert that into degrees, I'm just thinking about what's 3 times 180, because pi is 180 degrees, and that becomes 135. And because this is in the second quadrant, right, there's 135 here, what's the reference angle? What's the closest angle to the horizontal? Well, that's this one, and that's actually 45 degrees. So the idea with these exact values is that the reference angle will be the same, it will be the same magnitude. So I know this is going to be similar to sine 45, which is 1 on root 2. Just got to double check the quadrants though, and whether it's positive or not. So remember, all stations are central. So it's sine, and it's in the second quadrant. So it is positive. So I know that sine 135 is the same as sine 45, which means you still have to know sine 45, right? Which is 1 on root 2. So that's 1 on root 2 for that. But that's the process you use to check any kind of quadrant, right? And then sine of pi on 2, that's just going to be 1, right? And so that's kind of, finding exact values of these trig functions. Make sure that you're comfortable working with these angles inside here, because they can become trickier over time as well. Even for examples which can look at first intimidating, do turn out to be quite nice as long as we're comfortable with these exact values. So here's an example of what I mean, right? So here's a situation where I've got this expression here, it's sec squared, so I know I'm going to get tan when I integrate. What exactly am I going to get? Well, here, the thing that's different is I've got this pi on 6 thing. So I have to just be comfortable with adding these as angles when I actually integrate. But I'll show you that it turns out to be quite nice. When we integrate, we get no constants I have to take out, so that's just going to become tan of 2x plus pi on 6. Now remember, we do have to think about the a value. The a value is still 2 here, right? So I should take that out first. So it's 1 on a or 1 on 2. And that's from 0 to pi on 12, right? And so what I'm thinking here now is when I substitute this in, I'm just going to think about how do I simplify. So I've got 2 times pi on 12 plus pi on 6. And then I'm taking away that same thing, but now I substitute the x value. And again, this is a situation where the x value doesn't turn out to be 0, right? So just always make sure you sub in the 0 value. And what happens here? Well, hang on, 2 on 12. Hey, I know what that is. 2 on 12, that's just 1 on 6. So that just becomes half outside of tan 2 pi on 6 minus here. This part becomes 0, but then I get left with tan of pi on 6. Now, again, at this point, we can continue simplifying because part 2 pi on 6, that's just pi on 3, right? We put in your calculator. 2 on 6 is 1 on 3. So that's just going over here. And so this is a form where I know these exact values, right? It's great. That's why I say know your exact values. So it's just tan of pi on 3, and that's going to be, do I know my exact values? Root 3 minus 1 and root 3 here, right? Yeah, okay, just double checking I got that right. So make sure you know your exact values, and even something that looks intimidating first, as long as we take steps to break them down and simplify them slowly, we should be able to get them pretty good.